Hi students, here we're going to look at connecting what we have just done, finding the area under the curves, and move this into something called a definite integral. As usual, Khan Academy stuff should show up on your own copy of the Jamboard. All right, so here is something that we talked a little bit about in the last video. And the idea is to write things in terms of sigma notation and to kind of be able to go back and forth between the two of these. So I need to think about these visually in order to kind of process what's going on here. Just in terms of making sense of this. So let's look at the sigma notation first, in other words, this Riemann sum. So this is telling us that we're going to have an infinite number of pieces. Okay, so from piece 1 to the nth piece. All right, so that's looking at all of these pieces being put together. All right, we've got some kind of a function, f of, and then we've got 2 plus k times 3 over n. So let's figure this out. I see some stuff here that I can work with. The first is that we have some kind of a starting input value. That'd be like an x1. And then we're adding some kind of a change, which is this 3 over n thing, based on having an n number of pieces here. All right. All right, so I've got a starting value, that's 2. I'm going to write that as 2 there, just so I know what's going on. I'm also going to put an f of x here, because I know I'm going to have some kind of a function, and a dx, because that's going to be the, if we think about this as the height times the width of these rectangles, that's going to help us here. So the one piece that we really need here is to figure out what the upper bound is. And I'm going to try to make some sense. By the way, these are really hard for us as adult humans who have done calculus for a while as well, because they make our mind kind of bend around a little bit. And that's just kind of weird. So this is not something that's an easy thing to either do or to explain. But once you begin to notice some of the patterns, it gets a little bit easier. All right, so if we have this thing at the beginning. Okay, this is going to be the equivalent of my f of x here. This is my height. And if I'm multiplying a height by another number, that's got to be my width. Okay, so now this is the width of each rectangle. And it looks like we've got a total of 3 for that width, divided by the number of rectangles. N is always going to be the number of rectangles. So, thinking about this in that way, if we're starting at 2, and we're going 3 more, but we're breaking that into rectangles, that means that we're going 2 plus 3 is going to be 5, is my final value. This stuff on the inside, this is just kind of adjusting for every rectangle that we use. We are going 3 over n more to the right. Okay, and that actually came together kind of quickly there. I almost wasn't expecting that to happen. Let's see if we can go backwards. So we know we need a sigma. We know we need to start at the first rectangle and go to the nth rectangle. So that part's never going to change, and we know that the limit is going to be as n approaches infinity. You might remember on the previous one that we looked at like this, we had this set up as the limit as the width changed to 0 instead of the number of rectangles changed to infinity. It's easier to do this mathematically this way. In fact, I don't even know how to think about the other way. I'd have to really think about that. But we're not going to go there. Okay. So we also know we're going to have f of some kind of stuff, and then we're going to have some kind of a width at the end of this. All right, let's talk about the width first. So we're going from 1 to 5. That means we're going to have a width of 4 divided into n rectangles. So this is the width. I'm going to call that total divided into the number of rectangles. Okay. I'm going to have a starting value. So f of 1. And to that, I'm going to add whatever this width of these rectangles is. So that's going to be 4 over n. And depending on how many pieces, again, we count each piece, or we number them according to like k equals 1, k equals 2. So this is where our k comes in here. Once you do a few of these, you begin to notice that the process is really, really similar in just kind of setting up these problems to basically just convert back and forth. These have been showing up on the AP test, usually as one multiple choice question. I don't know that it's really worth spending hours studying this, although if you get some sense out of this, that's not too scary of a thing to do. It's just a little bit mind-bendy. Okay. So one of the things that we mentioned was that this notation, I'm going to just use this. So the integral from a to b of f of x is equal to the area under the curve between x equals a and x equals b. We also have to think a little bit about this because we're talking about the area between the curve and the x-axis, and there are times that we are both above and below. Area that is above the x-axis is going to be a positively signed area, and area that's below the x-axis is going to be a negatively signed area. So we have some areas that are positive and some areas that are negative, which is kind of weird. For these ones, we're going to use geometry to solve these problems. So looking at this one, we've got x over 2 plus 3. That starts at a height of 3 and has a slope of 1/2. We're going from -2 to 4. And in looking at this, so at -2, this is going to end up having a height of 2, and at 4, this is going to have a height of 5. This is really one big trapezoid, and I can break that up into a rectangle and a triangle pretty easily. It's going to have a width of 6 and a height of 2. That gives me 12. Width of 6 and a height of 3 is going to give me a area of 9. So the exact area under this curve would be 21. Ooh, from -1 to 1, 2 minus the absolute value of x. So we're starting at a height of 2. The absolute value of x is going to be a slope of -1 and 1 going each way. And that's going to go from -2 to +2. We care about from -1 to 1. And we're looking for this area. I'm going to break this up again into a rectangle and a triangle. And my rectangle, I'm going to change color so I can see, has 1, 2, so that's an area of 2. And then we've got 2 triangle pieces that have a height of 1 and width of 1 each. Together that gives us 1. This should be 3. All right, 9 minus x squared inside a square root. Many of you probably don't recognize this, but this is the equation for the top of a circle. This is a useful equation to kind of recognize where we have a perfect square number minus x squared. That would be for a circle with radius 3. And you might also notice that we're being asked to find the area under this curve from -3 to 3. So we've got area is pi r squared. My radius is going to be 3. So my area for a whole circle is going to be 9 pi. And then if we want a half circle, it would be 9 pi over 2. Okay, looking at the next one. Ooh, this is cool. So we've got y equals x. And we're going to a point. We don't know what point that is, but this is going to be b comma f of b. Oh, b comma b, because for y equals x, all the coordinates are the same. All right, so we've got a length of b and a height of b. The area for this is going to be b times b is b squared. Triangle it is b squared over 2. Cool. All right, absolute value of x. That's a fun one too. So again, we're looking at absolute value function from -2, that'd be -2, 2, to +1. And this area is going to be triangle plus triangle. This left triangle would have a value of 2, and the right one would have a value of 0.5. So 2.5 would be our total area. All right. Ooh, this one's even weirder than the other one that we just did. So the graph of y equals 2x. And we're going from the point A. I don't really know where this is going to be, so I'm just going to call that there for now. That would be a comma 2a. We're told that both a and b are positive, and that b is after a. And then we've got b here. And this is going to be b comma 2b. Okay. So we've got trapezoid triangle going on again. This would be b minus a for my width times 2a. All right, and then for the top part of this, it would end up being b minus a for my width. I'm going to just divide that part by 2. And then a height of 2b minus 2a. That's kind of weird. So, ooh, I've got a 2 there. So if I take a 2 out of here, I could cancel those out. That'd be kind of nice. Okay, so I guess the top part is b minus a squared. And then the bottom part is going to be b minus a times 2a. All right, that looks a little bit simpler, but I don't know if that actually is much simpler. Okay, I'll buy it. Ooh, so we've got this big thing going on here. And we're asked for a whole bunch of this stuff. Okay, so the first one is us to think about the area from a to b of f of x. And f of x is this parabola-looking thing. So we're talking about this area here. And the area going backwards. So if you think about one area going forward, the other area going backwards, these have different mathematical meanings. And if your first instinct is to think about this in terms of stuff being negative, you're right on the money. This is exactly what this is going on. So if we have the integral from a to b of f of x dx, that's equal to the opposite of the integral from b to a of f of x dx. We can use this property to kind of manipulate things into some pretty helpful ways. All right, I'm also going to erase my scribbles so we can talk about the next one. Number 2, the value of the integral from a to a. So the area under a single point. I don't think I can actually get an area there, because the area of something that's infinitely thin would have to be infinitely small, which would be 0. All right, so we're looking at the area from a to b of these things added or subtracted together. If we think back to, we know this is just a limit. And if we think back to the stuff we've been doing for quite a while, you might recognize this is going to be the area under f of x, that dx just kind of closes that off, plus or minus the area under g of x, depending on what we're doing. Again, we have to do a dx to close that off, so that we have our length times width each time. And that kind of makes sense to me as well. All right, the last piece, we want to know the area from A to C. We already talked about the area from A to B. So one of the things that we can do with integrals is to write things as integrals of pieces together. So we're thinking about this as the integral from A to C of f of x is going to be the same as the integral from A to B of f of x plus the integral from B to C. In other words, we're adding up those two pieces to make that whole area. All right, here's a great place to kind of practice some of this stuff. So we're being given some of this information. And our goal is to use some of those integral properties that we just talked about to make some sense of each of these things. So for A, we want to go from 4 to 1. We know the value from 1 to 4. We know if we switch those bounds, it's going to be the opposite, so this would be positive 2. Going from negative 1 to 4, well, we know from negative 1 to 1 and from 1 to 4, if I join these two pieces together, that would take me from negative 1 all the way up to 4. So I would think about this as 5 plus negative 2, just so I can see those pieces separately, and that would be 3 as an answer. For part C, these are things that are kind of broken up. So we've got this first one, which is 5, so 2 times 5. And the second one, we do have that integral from negative 1 to 1. That's going to be 7, so 3 times 7, and that would be 31, all things told. For part D, I'm trying to find the integral from 0 to 1, but in looking at this, I've got the integral from negative 1 to 1. I've got the integral from 1 to 4, and that's for f. H doesn't matter for that one because I don't have that. I don't know anything about the nature of this around 0 to be able to give that information. So we can't figure this out based on what we're told. For h of x, we don't know what type of function this is. We know from negative 1 to 1. An equivalent way to look at this would be to say, okay, this could be a horizontal stretch by a factor of 2. We don't know if this thing is symmetric. We don't know if it's quadratic. We don't know what type of function this could possibly be. So because we don't, this is another one that we can't actually do. And then for the last one, this is going to be a third one we can't actually do. And the reason is, well, we're okay with this first part, but for h, we only know from negative 1 to 1, so we can't actually follow through with that and figure anything out there.